So we can start recording, and if I now try to do that over a larger space, then it'll be even harder with the different brightness settings. Now, unfortunately, I have two versions. I have one that uses RGB minimum, maximum, and also one that adds another 3 difference channels. That works a little bit more reliable. You can try it out, but I haven't uploaded the version with the difference channels here. I mean, it's uploaded, but it isn't pushed yet to the GitHub website. And you can do me a favor with this particular project. If you have an iPhone, then I want to try and see if that actually works. Thank you. Because you can just go to this website and then you can, or click on it on Discord, and then you can run your own color predicate. So let me see Discord. And the user interface is simple. You can either adjust the sliders yourself if you want to, or just click on the pixels that you want to include in the color. And if you get it wrong, you have to reset it. Okay. Also, I posted some sample pictures that you can use for inspiration when you're trying to solve the assignment. So here, some pictures of the different objects that we want to have, coins. Right? You want to be able to make the coins appear and disappear, project different numbers on the dice, or playing cards. So we actually bought a set of large playing cards. You want the person to be able to move the card, and you want to replace the image of a queen of hearts or something like that on the card. And then you can go, now it's a king of clubs. You just have to make sure that you don't project it onto your hand while you do it. Okay. So I can actually select a different camera, and then what do I want to track? Anything interesting? How about the blue bottle? Can you just hold up the water bottle there? Oh, I missed it. Too small. Okay, yeah. So now try and be a soccer playing robot. Move back, move forward. Oh, okay, I still got you. Yeah, okay, now you're gone. Okay, good. Thanks. And since you should be interested in different technologies for doing this, this is using the React stack, which is the current framework, together with Vite, which is the bundler, so that's kind of like a linker for C++, OpenCV.js, the JavaScript bindings for OpenCV, and TS is TypeScript, because TypeScript is actually a pretty cool language. It makes JavaScript programming a whole lot saner. But I have to say, when you look at the looking at React programming is kind of an interesting feature, because here so before, the components that you render, like the parts of your application, in my case the camera and the blob detector, the two components and the app, it was sort of reasonable to understand what's actually going on, because you had a class, right? And then a class could be an object. You could have inheritance, so you can you can extend a class, and then you have superclasses and subclasses and things like that. That all makes sense. You have a constructor for a class, so you know what happens when the class is instantiated. You know when memory is allocated for it. You know when memory is destroyed for it, when you delete the class. And then you can have instance methods. Let me see, do we have one here? No. You can have instance methods. Now, this one I also don't understand why they believe that change color is equal to this arrow notation in order to define a function. That is already a little bit strange, because you can actually just write function change color with the brackets the way that you'd be used to in C++ or Python or any other programming language that came before the JavaScript wave. You would usually write it as a function, but okay, fine, so they want to have function pointers everywhere. But this sort of made sense still, and you have state, you can encapsulate state. Every time the state changes, the object is re-rendered, which is really the main tricky part in developing complex user interfaces. Right? You have many different sources of data. If anything changes, you need to update all the correct parts in your application. And that state could be distributed, right? Like you have a list of grants that I got, because I need to generate that list right now. Then you have the certain amount of money. Then you have another table somewhere, or a page that shows the biggest expenses that you had in the last 6 months. And now if you get a new grant with new money and you spend some more, then the new grant will have to update the maximum grants that you had over the last 5 years, for example. And if you edit that somewhere, the name of the grant, then of course that needs to be changed throughout the entire application. So this is a pretty tricky problem, especially if you want to do that performant. So you want to do that fast enough, right? Otherwise, of course, you could just bring the whole application down and then rebuild everything from scratch. But if that happens every time the user hits a key and says this is a current grant or open grant or a closed grant, if every time you click the button you have to completely rebuild the entire application, then that would be much too expensive. So nowadays, anything happens in your interface, there's like a whole bunch of changes that cascade through, and if that changes, then there's a whole bunch of dependencies that also need to be updated. So the problem is definitely non-trivial to solve, but the way this is done now in React is kind of interesting. So you can have a look at my application. And the funny thing is that the idea is that you simply don't have classes, but you have these functions that get called. And then that sort of, I can follow that part along, but then this is what the functions end up looking like. And this is my first React app, so maybe there's a better way to deal with this, but here is the actual code for the block detector, for the color predicate in TypeScript. And here, this is what I would consider a function, right? Function, it does one thing exactly, it applies the color predicate. There's a bunch of parameters, like a source image and a destination image, and then there's a color predicate, and it basically is the code that paints the pixels that match the color red, right? So that's what you see in the actual output. So that would be a reasonable function. But what you now have as a function here is for the block detector, starts at line 54 and goes all the way down to 421. So this will be an extremely big function. And then not only do you have the function, but you define various functions within your functions. So you have nested functions, and I understand closures. Like I actually programmed in Scheme and Common Lisp a lot, and I like them, but this seems to be too excessive. You specify things that are part of the state, so you can define your state variables, and then within your function you have another hooks that you can define, which are basically side effects of your pure functions. They need to be encapsulated, obviously, because the function in the React framework is kind of like a function in a functional programming language paradigm. But now you have all of this, and now basically you have a class, right? This is not really a function anymore. This is based, so if they had just left the class keyword there, then I guess that would have been a lot better, but you have a huge functions now. And the problem is, I really have no idea about the life cycle anymore. Like, when are these variables allocated in memory, when are they instantiated, when are they updated, and what happens when you update them. I think it's very tricky, very difficult to actually follow through the logic about exactly what happens when different things occur. But there you have it. That's the React framework. What is kind of cool is that you can define different components. So you have this HTML-alike syntax in order to define different parts of the applications that you can then include and exclude. So the other problem is if you have different programs, you want to merge them together, then the only way I see how to do that would be to have them as different HTML components, as different parts of your page, and then you can basically include them into the page. So here's one camera, and here's another. This is the actual color detector here that does the thing for the color. Other than that, what is pretty nice is, of course, the debugging support is actually quite good. You can just use DevTools in order to debug your application. That's kind of neat. So if you have an iPhone, let me know if that works or not, that particular application.
He only works with the camera. He cannot switch cameras.
Cannot switch cameras? Okay. But on the other hand, of course, that's pretty cool already. You can write one code and have it serve on Linux, Windows, Mac OS reasonably performant. Like fast enough to actually use for computer vision project. That's pretty neat. So today we want to talk about the Harris corner detector because we talked about different ways to identify edges. Talked about the Sobel, the first order operator, and the Laplace, the second order operators in order to detect edges. Now we're going to look at corners. But does it actually show the second camera? Like, do you have a combo box for camera 1, camera 2? No? Okay.
It's like this, it's empty for the camera selection.
It's empty, okay.
Yeah.
Yeah, I think I made a mistake.
The default is front camera.
Yeah. That's of course not so useful. I wanted to have the environment camera because then you could just put your phone there and you can track the ball during a soccer match for the robots. That would be pretty useful. So we look at some more interesting features now. Instead of just edges, we're looking at corners, but it's not strictly corners that we're looking for. It's called the Harris corner detector, but there's actually the definition of a corner in computer vision in that sense is a little bit more abstract. The idea is that we want to be able to have points that we can track through the image, and applications of that. The one that we're working with most of the time is the problem of visual odometry or visual SLAM. So let me think, what could I show? Oh, actually, I have that. So here's a scene that we recorded with our camera, with our robot. So this is our humanoid robot walking. So if you look at that video, then what motion did the robot do? Like, where did it walk to? Like turn left, turn right, forward, backwards, forward and turn left, forward and turn right. What did it actually walk? How did it walk? Huh? Forward, yeah. And you can also tell about the distance that it walked forward, right? About 3 or 4 meters. Now, turn left a little bit.
I don't,
right?
yeah, I don't lead. I am.
And the question is, how do you know that? Because we didn't actually see the robot, right? So how do you know that the robot moved forward here? Huh? Not necessarily beside it, but any object in view, right? It doesn't have to be the objects beside it. It could be, it's also, you can tell by looking at the left corner, for example, you can tell by looking at the door and some other features. So in this case, what we want to do is we want to track particular points through the scene, right? The basic idea of visual odometry and visual SLAM is that we track points as they move through the image, and then we calculate what motion the robot did in order to end up with this new view of the scene. Okay. Now, this is a difficult task in the sense that we don't really have good solutions to do that. In simple domains, we can do and over short periods of time, this works really well, or well enough for most applications. As the distances increase and the environment becomes more complex and also more dynamic, then the systems are less robust. If you do need to localize a robot, nowadays in 2023, I think you'd still be better off to add a laser scanner, a LiDAR scanner to your robot. Your localization is going to be much more accurate than anything you can get with the visual SLAM system. But they are getting better and certainly useful now for some applications. It's interesting to note that this kind of visual tracking is not just done by robots, but also by humans. Let me see if I find the video. Oh no. David Lee did research on this in
Once everything's perfectly
1974
organized, I'll start
already.
working on my thesis.
How important then is this visual information in maintaining balance? In most adults, even when doing a difficult task, the sway is small and balance is easily maintained. But if visual information is important, then it should be possible to upset a subject's balance in an experimental room by moving the room gently forwards or backwards.
So now they postulated that vision is also important for balance. At the beginning, people thought it's easy to verify that, because if you yourself try and stand on one leg and then you close your eyes, then it becomes more difficult to balance on one leg. So the idea was pretty much accepted, but they did some more studies on it. Now here, they built a room where they
Infants
can
learning
move
to
the room
stand are less
instead
stable
of
than the adult
the child,
and far more easily
and then
put
they
off
had a little
balance.
kid there.
The infant in this experiment has only been walking for a month.
So can only walk
When
for
we
a
move the
month.
room backwards, the child falls.
Now they move
And again.
the walls, and then the kid falls over because
In
it
92
doesn't
trials of this
understand that
type,
the visual
7
feedback
infants, balance was
doesn't,
clearly disturbed
come
in the
from
predicted direction in
See, so-
82% of the
So now it
trials.
stumbles when the walls start moving, even though
It
in
seems
the
then
kid itself,
that for the
baby
infant
is,
learning to
sitting
maintain
still.
balance, visual information
Oh.
is far more potent than mechanical information.
So actually, visual information is extremely important for beginning walkers.
But the adult, however, is less sensitive to conflict between visual and mechanical information, and movements of the room do not, as with the infant, knock him over.
So for adults, it's not a
But
problem.
let us give him an unfamiliar balancing task, such as standing on a narrow beam.
But if you make the task harder for humans,
With his eyes closed, he depends solely on mechanical stimuli, quickly becomes unstable and falls off. Or with his eyes open, if the room is moved, even slightly, he will lose his balance,
now
just as
people
the
lose
infant
their
did.
balance when they have a challenging balancing task and you move the room. So the more difficult, if the balancing problem is just to stand still on the ground or go through a common walking pattern, then no visual feedback is needed. But if you have a challenging balancing problem, a dynamic environment, then visual feedback is still very useful, very important. And if you mess with it and you move the walls, then people cannot balance anymore. So I thought that's pretty interesting sort of research out of psychology. So now, if we want to track points, if we want to be able to track the environment in order to do visual odometry, which means visual odometry just means picking up how you move, like 50 centimeters forward, I turn to the left by 20 degrees. Visual SLAM is visual odometry, plus you also build a map as you move around the environment. So at the end, you have a map of the environment. But the main component of it is the same. It's detecting movement in the environment. If I want to detect movement, then edges are not really good features, right? It's not a good idea to try and track the edges if I want to to detect movement because, for example, here, if I'm at this position here and I track this edge, this corner, and now I move a little bit closer, then all I really see is the same edge. I will not have noticed any displacement. So with an edge, however, if I rotate, then of course that edge would work really well, right? I can track how many degrees I rotate. So this is also called the aperture problem, but if I have an edge here, then I can very well distinguish or see if that edge moves left or right, but I cannot really tell if the edge moves up or down. Right? No idea whether it does or not. So that means that, and the same thing of course is true for horizontal edges or any kind of edge, sidewalk or something like that. You know how far away you are from the sidewalk, but you cannot really tell your forward speed along the sidewalk. So that means we cannot use edges. So really we want to find features in the image. If they allow us to do that tracking, then I need to find features that if they move in any direction, that I can notice that movement. So that means we need to have points. They cannot be features, but they also have to be special kinds of points. In particular, what we would like ideally would be points that are globally unique. But those are often difficult to find in an environment. They often don't exist. If we cannot get globally unique points, then our next best would be locally unique. So, for example, on the floor here, my robot uses the floor in order to detect its motion, then the crosses are very good features, right? They are very easy to track. I can also see if they move up and down, even though they are only locally unique. Like this one, this one, this one, they all look the same. They're all crosses, right? So, but the point is, if I move slow enough, then there should be no problem with me mistaking this cross for that cross. If I just move a little bit, then I'll still know this cross is the one that moved out. Not, I'm now looking at this one, or now looking at this one. Of course, if I have the eyes closed and I walk for a whole bunch and steps, and then I look again, then I don't know which cross I'm looking at. So when we talk about corners, then these are the kind of points that we have in mind, really points that we can track going through the image. And one way of getting that would be to actually have a corner of an object, like a corner of a house or something. But strictly speaking, that's not necessary. As long as the point is identifiable and trackable and locally unique, that's all that is really required. So it doesn't have to be the corner of an object, like things would be shadows shadows may be also, like this shadow there, which is not really a corner, that would still be a pretty good point to actually track. Because the shadow on the wall there, with the sunlight coming in on the back of the window, then that is not really the corner of an object, but it serves the same purpose. It would have the same feature. I could still very clearly identify where that is, and I can track that point throughout my movement. So basically what we want is points that if they move in any direction, then I will notice that. So how would I notice this? Well, I would notice this if the point, if I shift it a little bit, is very different from its environment, the pixels around it. Right? I want to have points that if I move them by a tiny bit, then I can, and then overlay them on the image there would look very different. And those would be the points that I want to track. Now we can actually formalize that using exactly this definition, right? So the idea is that we compute the sum of the squared differences between two parts of the image. One is the point that I'm considering as a feature point, and the other one is that point plus some small shift in delta x and delta y. And then for all the delta x's, delta y's, I want there to be a big sum of differences, squared difference. Now, I don't want to do that for the entire image, right? Because different parts of the object, of the points are at different distances, so they move differently. So we use the windowing function to sort of limit it. So that means I want to have a 5x5 patch or a 9x9 patch of the image. If that shifts, then there's a large difference to the background, to the unshifted image. Let me just try this one. It should work. So here would be our definition of a point. Anything that has a large sum of differences. So we sum up over the x and y's of our windowing function, and we take the either intensity or the red, green, blue components of the image at x plus delta x, y plus delta y, and we subtract from it the intensity at x and y. So that's how much change we got, and then we square it and sum them all up. Square it to make sure that they're all positive, and then sum them up. So that means I need to be able to calculate for if we think about the imaging function, and I consider it for one row, so let's say row is equal to 200 here, and then we go along the row. Here's my image function just in 1D. Then mathematically, I get to this point here, and now I want to say how much does this change if I shift that around and project it by delta x, that is by a small part. So that particular problem here, how to calculate the value, because I don't really know, right? Could be here, could be here, could be here. I need to predict where what the intensity is at the next. And there's, of course, different variations of that problem. Intuitively, let's say if your image looks like this, then what do you think would be the value here at delta x? X plus delta x. Then what value would you predict? Well, then I think it's pretty obvious, since we have a whole bunch of points that are all in one line, we would expect the next point to be the same. There's no reason to think anything else. Then here, for example, you may argue or you may think that this follows a linear sort of growth, so then you would expect it to be up here maybe, so on and so forth. So this projection has been studied extensively in mathematics, and the way to solve it is using the Taylor series or Taylor expansion. So now let's have a look at the Taylor series. Oh, and I guess one thing that came up that I forgot to mention is for the point on the shadow there, as far as visual odometry and visual slam is concerned, it's also a matter of time scale, right? If my robot is driving around here for 1 minute, then it can use a point like this for reference easily enough. It can use the shadow or the corner point implied by the shadow. If you do that for 10 hours, then of course the sun is going to go down and the shadow is going to move. And in fact, a lot of the visual odometry research right now, one of the big problems is not so much the finding feature points to track, but figuring out which feature points are actually static in the scenes and which ones are dynamic. So if you do self-driving cars, in order to detect the speed of the car, for example, then if there are trees or buildings, you can use the points on the buildings in order to track your progress. But if you have other cars and pedestrians, then of course you end up with a wrong result, because the velocity then would not just be your velocity, but also the velocity of the pedestrian or the velocity of the other cars, and it can greatly throw off your estimate for your visual odometry or your visual slant. So the Taylor series is a method, an algorithm for calculating the unknown value of a function at x plus delta x when we know the value of the function at f of x, plus we know the value of all the derivatives. It was found or developed by Brooke Taylor in 1700 or something like that. 1685 to 1731. And he developed the infinite sum that converges to the true value of the function. So this is actually correct, assuming that your function is infinitely, you can calculate all the derivatives, differentiable, infinitely differentiable, and that that it's continuous, which I guess is implied by the differentiable constraint. And then you can actually calculate the function. Now the first part, of course, is kind of not surprising. In this location here, if I'm at this point here, then I know the value of the function and I know the first derivative. That means I know the slope, right? The tangent to the function at that point. So then I can sort of say, okay, then we will project it to here. That would be the point that we predict. But of course, that's only sort of the first step of it. Then you can look at the second derivative, which tells you how much the function is going to, how much the derivative changes. And then that would allow you to adjust and come up with an even more accurate estimate of the value of the function at f x plus delta x. And then you can look at the change in the change of the function. That will be the third derivative, so on and so forth. And these different components have to be weighted, and that's sort of the main, the tricky part here, or the part that that is non-obvious, and I don't actually know the proof for why this is the correct one, but the factors increase as a factorial. So the first derivative is 1 factorial, the second derivative is 2 factorial, the third derivative is 3 factorial, and also the distances like this delta x, which is a small number, is then squared, cubed to the power 4, 5, so on and so forth. So looking at the Taylor expansion, it's clear that really the more successive terms, the influence of the higher level terms is going to decrease exponentially. It's going to, the weight is going to be quite small because A, we're dividing it by the factorial here, and B, also delta x is small, less than 1, so if you square that, you get a number that's much smaller than 1. So to show the use of the Taylor expansion, Taylor series, we can use the SymPy system and Python, which is actually really cool. It allows you to do symbolic mathematics in a Python program, and then also evaluate function, do some actual computations with it. So we import the SymPy as sim, and then we say that we want to use Unicode characters for our printing. That's just to make it look a little bit nicer. Oops. Then we define a variable x, which has the symbol of x, and then I can define a function in 2x to the power of 5 minus 2x cubed plus 4x squared plus 2x plus sine of x plus 1 plus a constant term of 20. And so, SymPy actually knows enough in order to be able to symbolically calculate the derivatives of this. So sym.diff is the calculate the derivative, and then we can pretty print them out, and this would be the output that we get. This is f of x, f dash of x, f2 dash, f3 dash, f4 dash. I guess I can do it like that. This is f dash, double dash, for quadruple. And here's f of x. That doesn't look so nice. Let's try that. Cannot really put that on one line. We can plot it like that. So f of x is 2x to the power of 5 minus 2x cubed plus 4x squared. Then 2x to the power of 5, the derivative of that would be 2 times 5, 10 multiplied by x to the power of 4 minus 6x squared plus 8x plus cosine x plus 1 plus 2, and so on and so forth. So now this Taylor expansion is not the only way to try and estimate what the value of the function is at some unknown point. The more common approach is interpolation, and then we can look at different ways to do this interpolation. So the simplest form of interpolation would be simply to take the nearest neighbor approach. So I just take the value of the function to the closest point where I know the value. Then we can add more complex interpolation. Linear interpolation is very popular. So now here I can calculate the Taylor expansion of my function, which simply takes a function and also generates a subroutine that I can call with the value of for x, and then it returns the actual number. So now I have the symbolic expression 2 to the 10 times x to the power of 4, and I also have def f of x colon return 10 times x to the power of 4. So I get here the Python code that I can run. Here's the symbolic expression. And this just calculates the Taylor expansion for a particular function. So here I can pass it in for a value of 3, up to a level of 3. And these are the functions that I get. 0 is just the function itself. Then first derivative, second derivative, third derivative, so on and so forth. So then we can plot it. So here would be an example. I have a function in blue. The function is unknown. I can sample the value of the function at certain points. Similar to our image function, we can get the value of certain pixels. And now I want to know what's the value of that function on at the red line, like where x is equal to the red line, which is, I forgot what it is, 1.2. Yeah, 1.2, 1 plus 0.2. So, and I can change that, make that 0.25 to shift the red line a little bit to the right. Actually, this is the point that I use. So now I go through and I interpolate that function using the nearest neighbor, which means I go through the known points of that function. I look for the closest one, and then I use that particular value in order to estimate. So I do a binary search, I find the point that's closest, then I check which one of them is actually closest to mine, and then take that value depending on which one of those is higher. So here this is the distance from x to the low point and to the high point. And if the low point part is smaller, then I take that value, otherwise I take the one for the high point. So for the function that we have, this will be the nearest neighbor approximation. You can see that its error is very high, right? 1.8 million. 1880214.93, so it's a very large error there. But you can also see that actually most of the error is not where I actually have points. In this area here, it actually does a pretty good job, but in the part where there's nothing, no other value that I have, then here to the left and the right, the error increases dramatically. Because here it's 6,000 and I say it's like close to 0. Then I can improve that a little bit. I can say, okay, I want to do a linear interpolation for those points. So now the point is calculated as using the estimate of the slope from the point to the next point. And then that shows the linear interpolation. So you can see instead of the blue line, which sort of is, they're all horizontal for nearest neighbor, then it drops down. Here we do a much better job interpolating it using the brown line. Also at this point here, where the slope is about 45 degrees, so the slope is about 1, the brown line follows the blue curve a lot better than the blue line here, the light blue line. The error is not that much better because, again, most of the points are here and here where I don't have any successor points. So the interpolation there doesn't really work, so it just keeps assuming that it's the same value. Now if I apply the Taylor expansion to this, then I can calculate the derivatives up to a factor of 6. So this would be first derivative, second, third, fourth, 5, and 6th derivative. Then we can plot that. And now we can see how the error dramatically decreases. For the Taylor expansion at the first level, it's similar to the linear interpolation. So that would be similar to the zeroth approximation. Okay, so this is not the first, this is without the first order term. So that's similar to nearest neighbor. Second one is similar to the linear interpolation. Then Taylor level 3, 4, and 5 do much better. As you can see here, the last one, the purple one, actually has a very small error, 435.69 as opposed to 1.8 million. And here we apply the Taylor expansion. So here we add our factorial of level I, and here delta x is going to be set to the power 1, 2, 3, 4, 0, 1, 2, 3, 4 as we go through the system. Now when we talk about interpolation, then the more points we have, the better the interpolation is going to be. For the Taylor series, that doesn't really matter. We simply need to know the derivatives at the f of x. The derivatives scale with the factorial, so let me call that level. So the higher order terms are going to have less and less impact on the final output. Decreases exponentially. So up to level 5, that is already very ambitious. Most practical algorithms, we don't go that deep. 5 factorial is 120, so that means the term is only 1/100th that of the first order term. So it already has very little impact on the final number that is being calculated. So let's go back to our Harris corner detector and see how that applies for our, in order to detect corners. So f of a is the point that I know. X is the point that I want to interpolate. I can also rewrite that as x plus some small displacement. It's equal to the value of x plus our first order term plus the delta x. And then second derivative divided by 2 factorial multiplied by delta x squared plus f third derivative divided by third factorial multiplied by delta x cubed. And we can also expand that in 2 dimensions. So here this would be in the 1-dimensional direction. For 2 dimensions we need to do the Taylor series in both directions, and follow the derivative in the x and the y direction and the various cross components of that. So we start out we want to evaluate the function at x plus delta x, y plus delta y. Then we start with the point that we know, fx, y, and then fx, xy multiplied by delta x plus the component for delta y. So fx and fy here are the partial derivatives of the function, the multivariate function, the 2 parameter function f, one in the x direction and the other one in the y direction. And there would be a 1 over 1 factorial term here. Then for the second derivative we get 1 over 2 factorial, then we multiply that by delta x squared, direction, both directions, x, or second derivative in the x direction, second derivative in the y direction, and then the first derivative, also the cross term like x and y first. Now mathematically that should be the same as calculating the gradient in the first derivative in y first and then in x. So that's why we have the xy term here. And then for the third derivative we get even more terms, fxxx, fxxy, fxyy, fyyyy. So this would be the different derivatives, and then we can add the other terms. We could extend this. Now calculating the higher order derivatives can be expensive, and so in order to speed up the computation, and given the fact that the higher order terms have less impact on the actual output, we simply use the first order terms only. And then going back to our definition of the feature for our sum, for delta x and delta y, we can plug that in, right? So that would be ixy plus delta x, the first order term here, plus delta y, in order to estimate what the value is at I x plus delta x, y plus delta y, right? So this would be the first, the Taylor expansion up to level 1 for x plus delta x, y plus delta y. Then we subtract that from the known value I, x and y, and square it. So the I, x and y cancels out here. So the actual intensity at that point is not important. And then we get delta x, ix plus delta y y, that squared. We can expand the square, so we get delta x squared ix y squared plus 2 delta x delta y, first x, then y derivative plus delta y squared, y derivative squared. So this would be our equation here. But now mathematicians like to come up with more and more concise representations. So we can take out the delta x, delta y and convert this one equation into a matrix equation by taking out delta x, delta y, having ix, which is the square of the first derivative in x, the square of the first derivative in y, and then this cross term, first in x, then in y, and that's the same as here. So those two terms are the same, and then multiply that by delta x, delta y. If you actually expand this matrix equation, you end up with exactly this one here, right? Because you get delta x multiplied by ix squared, y squared plus delta y multiplied by this term, and then that multiplied with delta x gets you the delta x squared, ix y squared, and the two cross components. So that means that our sum, the result, the response that we get, can be written in this form, with M being a matrix based on the windowing, which consists of those terms. So Wxy is a windowing function, so we look at the 3 by 3 neighborhood, or the 5 by 5 or 9 by 9 neighborhood around that pixel, and then we calculate these changes. Now Harris proposed the following corner detector. The determinant of this matrix M multiplied by some small, subtract from it some small constant, the trace of M squared. And K is some constant that you can tune. The range is in the range of 0.04 to 0.06. And that's our corner detector R. And if that R is large positive, then you have a corner. So we want to threshold this for large values of R. If it's a large negative, then we have an edge. And if it's close to 0, then we have a flat region. So we can get some images here. And then let's have a look at our corner output. What's not? Oh, this is wrong. So this doesn't work anymore. And let's see. Like any computer vision researcher, let's take the Lena picture. So here's our picture, and then we can calculate our Harris corner detector. First, we apply the Sobel edge detector in X and Y. So here, this is implementing the convolution from scratch, like without using any libraries. Which is why that is a little bit slow, and so here's the output of our Sobel edge detector in X and Y. And then we can calculate the Harris response. And the weights that we have here is a 9 by 9 matrix. And here's the output of our Harris corner detector. Those would be the pixels that would be good to track or easy to track using any shift in the image. We'd be able to find them reasonably well. And we can also rerun this on a checkerboard pattern, just out of interest. So here's our checkerboard pattern. Now we calculate the Sobel. And that's almost perfect, right? The response here. The different colors are because for the checkerboard this goes from white to black, this one goes from black to white. So the sign of the response in the edge direction is different. Here similarly, white to black, black to white in the checkerboard. But other than that, the response is very good. Then let's see what we find for corners. And here are the corners detected by our corner detector. So you can see that it does a really nice job there. We also get the lines because any line, any edge would have a very strong negative response. The uniform colored areas are sort of gray. Now, just out of interest, if you look at the Taylor expansion series, then any kind of interpolation here, linear interpolation, for example, does a pretty good job with approximating the function. The big problem is that we get a huge error if we don't have any more points. But in the image, we could certainly, for x plus delta x, we could also always just pick the linear interpolation. Basically, that's what we're doing when we're using the Taylor expansion up to the first level only. Right? So I was thinking if we could just use the Sobel edge detector and use that in order to detect corners, then what the result would be that we actually get. So let me just implement that idea quickly. And then we'll see. So that will be f of maybe if we want to make sure that it's let's just square it here. To make sure that we have positive response only, and it will emphasize stronger gradients some more. So let's see what happens if we implement that. Now, one thing is, this is definitely a lot easier to implement than calculating the determinant. Oh, then I only get 1 point. Because that scaled too much then. Actually, I have a point there. Yeah, so I actually end up with the same points. I mean, for the grid pattern it works very well. I need to make that picture larger though. Let's try that one again with the square. That would be even faster probably on a modern CPU. So should be this. Too small. Here are points, and yeah, works very nice for the checkerboard pattern. It will be the perfect response. Why? This is made small a little bit. Because of the windowing function where we use the +9. And it up all of those. And here we only get it for the individual pixels. And that's a little bit harder to see. So if I wanted to do that, I would blur that with a wave. So if I want to have a windowing function, then I can do that. Product of the gradients. Dot. 9 by 9, so that will be 4. Half of that. Would be -8. Minus I plus 9. Just need to sum up over those, I think. I think it should be -9. Let's run that. I think that's the color image. Now that should be clear. Yeah, so this works pretty much the same in this particular case. Now I want to, now I want to use the planar image and see how it responds. that. Okay, so here, that's the difference between the proper edge detector and my little idea. If you compare this image, we do get strong responses in the points that are corners, like in the hairs there. But we do get very weak responses on the edges. Whereas if I simply multiply them, then I get very strong responses here. So this would not be a good corner detector, this approach, right? Because there we do get, and when you think about it, that makes sense, right? We do get a strong response if the edge is at a 45-degree angle, if it continues. So here I do get these points, so those are nice, but these lines, these edges here would be a very poor response for an corner detector, right? Because it's basically an edge, and that doesn't allow me. So that's why we need to have a more sophisticated algorithm. That's why multiplying the gradient together in x and y doesn't work. For horizontal and vertical edges only, the algorithm works just as well as the Harris corner detector. There's no difference really. It will find all the cross points. But the 45-degree slope lines will cause a problem, that's true. Because then you do get a little bit of an edge in x and a little bit of a gradient in y. So you do get the edge, so you get a strong response in both of them. So what you must have is really one that is very strong, the other one has to be close to 0 or the other way around, but not halves for that slope. Okay, good. So that's it as far as the class is concerned for today. As an exercise, implement the Harris corner detector and run it on one of your own images. You can use the OpenCV Harris detector, and one thing you want to do is check how fast it can actually run. So time your OpenCV Harris corner detector on any image that you want to process, and then see whether you would be able to maintain real-time performance, let's say at least 60 frames per second, using, still applying the Harris corner detector. Okay, so you can start with that. You can use the images that I used, the Lena image or something else, but for the next 45 minutes, use the OpenCV Harris corner detector function or the assert corner detector if you like that one better, and time it to see how fast it can run.
I think next time we should use that webcam because I just knew that webcam already have microphone built in.
Sure, I thought they all have microphones built in.
I think this one,
No? Okay.
because it should be short. Okay.
Oh, but I'm sure I'm sure it's from the webcam because I get audio.
No.
Yeah. Say something, then the green bar goes. It's just my Discord, I turn it off because otherwise it's going to generate feedback. Hello, hello, hello. If you have it still on, then you should be able to, you will get the feedback. I think both of those cameras have microphones built in. Yeah. And this one here too, like I can see it. What is this? How did this come up here? Got that along there. I think I need to convert it to floating point. U channel 1 4. So what is this then? And then I dot detail. Oh. Float 64. Oh. Yes, because how come I in a gray? Here. So let me try this one as CV dot convert color. And then image dot opens. Yeah, that should be UINT 8 now, so that should work. Okay. So that should make it a little bit faster. And what did I want to do? I wanted to threshold. threshold is. Blue, okay, so we add blue points. Red ones, and that should be that. I want to show the Harris response and the actual corners detected after thresholding. Image. Flip the channels. Okay. Now I have that. And let's multiply it by 0.3 to make it darker. 0.2. $64. Dilate. So here we get OpenCV Harris corner detectors with a value of 1%, so 1,000. Okay. No. That's why. So yeah, we get the same points that we calculated, basically. Let's use 0.2. So maybe I don't want to dilate it. And the blue points are a little bit hard to read. So I wanted to KS type. So I darken the image. Convert it to UINT8. I do need to dilute it. Yeah. So now I just want to time it. mp dot random dot Oh. That wouldn't work, right? Because that's 0 to 1, so random. From 0 to 255. And we can let that run. No, I mean, you're supposed to time it. It's a timing function. Because it's a very useful function to help you how fast your timing will run. And sometimes, especially if you deal with number arrays, you end up doing something that is really, really slow, or you get lucky and do something that's really, really fast. So Python, the time module is very nice. It can tell you how fast your code is executed. Even though in my case now it's a little bit conditional as well. Because it repeats the code 1,000 times to get better statistics for the work. Then you can type your assignment. I don't know, I think the performance is fine, maybe the performance is correct. You need to import the timing module. There's a module called import time, and that allows you to check how fast. It'll tell you every time you call that function, it's 12 milliseconds. So it's a very useful tool. Oh, you can do it this way too, of course, yeah, that's fine too. Timing is a little bit more clever, let's say, how to check some of the dates. Then run the routine a couple of times to make sure that there's no cache effect or effects loading the program from that part of the system. And then it runs that a number of times and calculates. But most of the time, yes. If you run this a number of times, so what time do you Yeah, it should be very fast. On a modern CPU, time is in seconds. And then 900 microseconds. Yeah.
The time you want is when including loading and showing the picture or just
No, just on a 0.0033. Yeah, so you have some more fluctuation. Well, you do the full conversion. Actually, I thought just this one line, but it's okay. It doesn't really matter what you measure, as long as you measure something to show. And yes, it would be fast enough to do real time. It wouldn't impact your real time performance. What you have right now is 9 milliseconds. Right? So, actually 9 milliseconds wouldn't be able to maintain 60 frames per second. That would be 7 milliseconds. No, 15 milliseconds. Actually, timing things and estimating the runtime of your algorithm is also non-trivial. There's quite a few caveats to keep in mind. Things like whether it's already in the cache, whether it was executed the first time, whether the just-in-time compiler had already had a chance to compile it or not, can greatly impact the performance of your algorithm. Repeat, what is it? Number. Okay. Seconds. Yes. So when I called it first, it was executing it 1,000,000 times the statement, which is why it was problematic. And then globals. Okay. So I think I can do that without the setup statement. Image is equal to np.random.randint 0255. That's why. How big is that image? Of course, it depends on how big the image is. So I create a random image of size 1000 by 1000 pixels. That's why that is a little bit slower than if you use the Lena image. So that's, for me, for that size, it's 2/100 of a second. So would be 50 times per second. That we could count. Not image, figure. And here we have that.